Welcome back to AI Paper Podcasts. We're the place you come to cut through the academic jargon and really get to the heart of the latest AI research.
That's the plan.
And today, we are digging into something pretty exciting, Qwen Image. It's a new foundation model that's making some serious waves in image generation and editing.
Oh, absolutely. It's a big one. And hey, if you just need the quick version, the 1-minute summary for your feed, here are the 3 key things to know.
Go for it.
Okay, first, Qwen Image nails text rendering, like really nails it. We're talking complex stuff, multi-line text, different layouts, even non-English languages like Chinese. It gets them right with amazing accuracy.
Yeah, that's a huge step up, isn't it, compared to models like, say, GPT Image 1 or Seedream 3.0, which often give you that sort of jumbled text look.
Exactly. Second big point, image editing. It's incredibly good at it. When you ask it to change something, it preserves the meaning, the semantics, and keeps the image looking visually real.
So like if you ask it to remove someone from a photo, it doesn't just leave a weird blob.
Right.
Or if you change a pose, the person still looks like themselves.
Precisely. It understands the context. And third, the performance is just really strong across the board on lots of different benchmarks.
Okay.
It even managed to snag 3rd place in the AI arena, which is human evaluated, right?
Yeah.
Competing against top commercial APIs. So it's a seriously powerful open source model designed to bring image understanding and generation much closer together.
Awesome. So that's the quick hit. For this deep dive, our mission is really to unpack how Qwen Image pulls this off. We want to explore the tech behind it, its approach, and what this might mean for multimodal AI down the road.
Yep. And we're basing all this on their research paper. It's packed with details on the architecture, how they trained it, loads of results, comparisons, the works.
Right. So let's start with the problems. What were the big challenges Qwen Image was designed to solve? Because image generation isn't exactly new.
True, but there are persistent headaches, especially with what the paper calls complex prompt alignment in text-to-image generation.
Ah, yes. The struggle is real.
Yeah.
You ask for specific text, maybe multiple lines, maybe in Chinese, maybe placed on something in the scene. And you often get, nonsense. Garbled letters, wrong words, text floating weirdly. Even top models like GPT Image 1 and Seedream 3.0 have stumbled here. It's surprisingly difficult.
That AI soup text, yeah. Okay, what about image editing?
That's got its own set of tricky challenges, kind of a two-pronged problem, really. First is visual consistency.
Meaning?
Meaning, can you change just one specific thing like someone's hair color without messing up their face or the background completely? You want targeted changes.
Right, no unwanted side effects. And the second part?
Semantic coherence. This is about keeping the overall meaning intact when you make bigger changes. Like, if you change someone's pose, does it still feel like the same person in the same scene? Does the story of the image hold together?
Gotcha. It needs to understand the what and who as well as the how. Exactly, and this is where Qwen Image really starts to shine. Their strategy isn't just one single trick, it's this comprehensive approach. Think meticulous data engineering, clever learning strategies, better training methods, and even optimizing the hardware setup.
Sounds like a whole system approach.
Yeah.
Let's get into that architecture then. That seems core to how it works. You mentioned 3 main parts.
Yeah, the core components are a multimodal large language model, or MLLM, a variational autoencoder, the VAE, and a multimodal diffusion transformer, MMDIT.
Okay, starting with the MLLM, they use Qwen 2.5 VL. What's its job here?
Its main job is to understand the text input, the prompt. It acts as the condition encoder. And using Qwen 2.5 VL specifically is key.
Why that one?
Because it's already really good at connecting language and images. That pre-alignment is crucial. It understands language well, and importantly, it can handle both text and image inputs. That's vital for the editing features.
Ah, so it can look at an existing image and read instructions about it.
Exactly, and they even tailor the instructions. It gets different system prompts for generating from scratch versus editing an existing image. Gives the model clear direction.
Clever. Okay, next up, the VAE, the variational autoencoder, the image tokenizer.
Yep. Its job is to take an image and compress it down into a compact representation, like a digital fingerprint, the latent code, and then later it decodes that fingerprint back into the final image.
And there's something unique about their VAE, right?
It's got the single encoder, dual decoder setup. One encoder handles both images and videos.
Oh, interesting. Planning ahead.
Seems like it. paving the way for video models. Then it has separate specialized decoders for images and videos, and critically, they fine-tuned that image decoder specifically on images packed with text.
Like documents and stuff.
Exactly. Real-world documents, slides, synthetic text blocks covering different languages, alphabetic and logographic like Chinese. They really trained it to see text clearly.
And they found something interesting during training about artifacts.
Right. They found that focusing on reconstruction quality balanced with perceptual quality really cut down on those weird grid patterns you sometimes see. And once the reconstruction got good enough, trying to use an adversarial loss like a critic network didn't really help much anymore.
Huh. Like the VAE got so good at its job, the critic couldn't find meaningful flaws.
Pretty much. That meticulous VAE tuning is a big reason why the text rendering is so sharp.
Okay, that leads us to the third piece. The multimodal diffusion transformer,
Yeah.
MMDIT, the backbone.
Yeah, that's the core generative engine. It's a diffusion model, and its job is to learn how to actually create the image based on the inputs it gets.
And it gets inputs from both the MLLM and the VAE, that dual conditioning thing.
Precisely. It takes the semantic understanding of what the image should be about from Qwen VL and the fine-grained visual details how things should look from the VAE encoder.
So it balances meaning and appearance.
Exactly. Semantic coherence and visual consistency working together. They also introduced a neat technique called MSROROPE, multimodal scalable ROPE.
ROPE, rotational positional encoding.
Yeah, but this version is adapted for multimodal inputs. It helps the model understand the positions of both image elements and text elements together, starting from the center and arranging text diagonally. It's apparently key for scaling to higher resolutions and getting that text-image alignment just right.
Wow, okay. That architecture sounds complex, but really integrated. None of this works without data, though. You mentioned data engineering earlier.
Oh, hugely important. They gathered billions of image-text pairs. But crucially, the paper stresses it wasn't just about the number. Quality and having a balanced mix were paramount.
What kind of mix?
They broke it down into 4 main areas. About 55% was nature, landscapes, animals, objects, food, etc. Then around 27% was design.
Design, like that.
Posters, user interfaces, slides, diagrams, art styles. Basically stuff with structure and often lots of text and complex layouts. That's a really important category for training text rendering.
Makes sense. And the other two?
People and synthetic data. Having this curated mix helps the model handle a much wider range of prompts and styles effectively.
And how do they even label all that data? Billions is a lot.
Get this, they use their own MLLM, Qwen 2.5 VL, as a super-powered captioner.
Using AI to train AI.
Pretty much. And it didn't just write basic captions, it generated structured metadata JSON format capturing object details, relationships, context, even transcribing text verbatim from the images.
That's incredibly detailed.
Yeah. Then they cleaned it up further with expert rules and some light AI classification, like checking for watermarks. It's a very sophisticated data pipeline.
Okay, but what about text, especially non-English text or specific layouts? That's often rare in typical web data.
Good point, they knew that. So they developed specific strategies using synthetic data to boost text capabilities.
Yeah, that work.
3 main ways. First, pure rendering. Basically taking clean text from good sources and rendering it on simple backgrounds with different layouts, focusing purely on character quality.
Just the text itself.
Right. Second, compositional rendering. This is smarter embedding synthetic text into realistic photos, like text appearing naturally on a sign or a piece of paper within a scene, teaches the model context.
Ah, so it learns text in situ.
Exactly. And third, complex rendering. This used templates, think PowerPoint slides, UI mockups, and programmatically edited them. Great for learning complex layouts, multi-line text, controlling fonts, colors, that kind of thing.
So they really attack the text problem from multiple angles using synthetic data.
Absolutely. It was crucial for handling those harder, less common text scenarios.
Okay, architecture data. What about the actual training process? Must have been massive.
Huge. They used a producer-consumer framework for efficiency.
How does that work?
It basically separates the data preparation tasks like VAE encoding, loading data from the actual model training. The producer handles data, the consumer trains the model, they run asynchronously so the training GPUs aren't sitting idle waiting for data.
Smart optimization. And distributed training, I assume.
Oh yeah, a hybrid approach using both data parallelism and tensor parallelism, leveraging libraries like Megatron LM and Transformer Engine. They made an interesting choice there, too.
Bushwiss.
They opted for distributed optimizers instead of activation checkpointing to save memory. Checkpointing would have saved memory quite a bit, actually, but it slowed down training step significantly, like almost 4 times slower.
Wow. So they prioritized raw training speed.
Seems so. A practical choice for such a large model. Then the training itself happened in stages.
Multi-stage pre-training.
Yeah. Progressively increasing the image resolution, starting small at 2506 by 256, and going up to things like 1328 by 1328. Helps capture finer details, also helps balance the data mix, avoids overfitting to one style or resolution, and lets them mix in more synthetic data where needed.
And after all that pre-training, it's not done yet?
Nope. There's a refinement phase. First, supervised fine-tuning, SFT, using high-quality human-annotated data to boost realism and finer details.
Okay.
And then reinforcement learning, using methods like DPO and GRPO, guided by human preferences.
How does that work?
Yeah.
Showing it good and bad examples.
Basically, yeah. Showing it pairs of images rated best and worst for a given prompt helps it learn what humans actually prefer, aesthetically and semantically. They even use some advanced math, reformulating sampling as a stochastic differential equation to allow for more natural exploration during generation.
Okay, that's a lot of careful engineering and training. So the big question, did it all pay off? Let's talk results. The AI arena.
Right, the AI arena. It's this open benchmark where models compete head-to-head judged by humans, uses an ELO rating system like in chess, thousands of prompts, hundreds of evaluators.
And Qwen Image landed.
3rd place overall, which is remarkable because it was apparently the only open source model mixing it with the top commercial giants like Google's Imagen 4 Ultra and Dream 3.0. It significantly beat out GPT Image 1 and FLU X.1 context there.
That's a huge validation for an open source effort. What about specific quantitative benchmarks?
Yeah.
VAE.
The VAE showed much better precision, especially on images with small text. Things that were blurry messes with other VAEs became legible with Qwen images.
Okay, and general text to image.
Top scores on a benchmark called DPG, showing it's great at understanding prompts with lots of attributes. And on Geneval, a well-known one, the base model beat the state-of-the-art. After the RL fine-tuning, it hit 0.91, the first foundation model reported to break the 0.9 barrier there.
Impressive, but the real standout was text rendering, right?
Oh, definitely. On one IG bench, which tests both English and Chinese text, it got the highest overall scores, dominating the alignment and text categories, like 0.963 on Chinese text accuracy. That's incredibly high.
Wow.
Same story on a new benchmark. Chinese word highest accuracy across easy, medium, and hard Chinese characters. And for long text, on long text bench, it topped the chart for Chinese and was 2nd for English. It just handles text way better than previous models.
Okay, so generation and text are clear strengths. How about editing?
Also top tier. It ranked 1st on Get-It bench for editing based on both English and Chinese instructions. Shows strong multilingual editing. And on MGetIt, across 9 common tasks like adding or removing objects, it got the highest overall score, just edging out GPT Image 1.
It seems like a real all-rounder. Anything else?
Yeah, a couple more things. State-of-the-art results in novel view synthesis, generating different viewpoints of something, and really competitive performance, even SOTA on some metrics, for depth estimation, which is usually a computer vision task, not generation.
So it's using its generative abilities to perform understanding tasks.
Kind of, yeah, it's demonstrating this idea of generative understanding.
Let's visualize some of this. The paper had examples, right? What did they show for text rendering?
Really striking comparisons. For like a long paragraph of English text, Qwen Image produced it clearly, realistically styled, no missing or garbled words. GPT Image 1, in contrast, messed up words like lantern and unfurling. Or another one, a complex slide layout with text in 7 different places. Qwen Image got them all right. GPT Image 1 missed one section entirely. Dream 3.0 distorted the text.
And Chinese text.
Even more impressive, arguably. It correctly generated intricate Chinese couplets where others failed badly. Another example showed an anime scene with text on store signs. Even handwritten text on glass Qwen Image rendered it all accurately. Others just couldn't handle that complexity.
That level of text control is really something. What about generating objects or scenes?
It did great there, too. Generating 12 zodiac animals in a specific plush toy style, it nailed the style, while GPT Image 1 failed on that. Or generating billiard balls with mixed English and Chinese text on them correctly arranged.
Spatial relationships, like putting objects relative to each other.
Yeah, it handled those well. Climbers interacting on a tree, a pigeon on someone's shoe, a pocket watch next to a cup. It got the positioning and interaction right where other models often misunderstood or placed things randomly. Shows a deeper grasp of scene layout.
Okay, shifting to editing examples. Changing text.
There was a cool one, changing graffiti, that said, "Hope to Qwen," while keeping the exact same street art style. Both Qwen Image and FLUX.1 pulled it off, but then Qwen Image also managed to generate a very specific enamel-colored glass art object when asked something the others couldn't render accurately.
So it handles style transfer and specific material generation. What about adding or removing things?
Adding a cartoon cat and dog into an existing photo, Qwen Image did it seamlessly, matching the style and lighting. Removing people from a crowded scene, most models could do it, but Qwen Image apparently excelled in maintaining consistency in the background fill-in.
And pose manipulation. That sounds tricky.
Very. But Qwen Image managed to change a person's pose while keeping fine details like hair strands looking consistent and, crucially, keeping the background stable. It even correctly inferred and rendered silk trousers visible through a side-slit dress after changing the pose that implies a level of subtle 3D reasoning almost.
Wow, that's beyond just 2D pixel manipulation. And chained editing, one edit after another.
Yeah, it shows strong performance there too, like extracting just the pattern from a piece of clothing, then zooming in, Qwen Image kept the texture details sharp. Or a sequence, place paper boats on water, then add large cargo ships in the background. It handled the whole chain, preserving the scene's integrity.
Okay, so pulling back from the specifics.
Yeah.
What are the bigger implications here? This feels like more than just a better image generator.
I think it is. It really shifts the goalpost. It's not just about photorealism or that generic AI aesthetic. It's about precise control, deep understanding, and especially getting text right. That alignment is key.
And that enables new kinds of interactions, right? You mentioned vision language user interfaces, VLUIs.
Exactly. Think about times when just describing something complex in words isn't enough for an LLM to really get it, especially visual details or layouts. A model like Qwen Image, integrated into a VLUI, could generate the visual representation, text and all, making complex ideas instantly understandable. It's a move beyond purely text-based chat.
A more multimodal way of interacting with AI.
For sure. And this idea of generative understanding is powerful too. The fact that it can do tasks like depth estimation so well, not by being trained specifically for it like a traditional vision model, but by learning to generate realistic scenes. That suggests a new path towards unifying understanding and generation in AI.
Interesting. And you mentioned its potential beyond 2D images.
Right. Its strong performance on novel view synthesis and pose editing, where it maintains identity and background coherence, really hints at its potential as a foundation for 3D and maybe even video generation down the line.
Especially with that video-ready VAE architecture.
Exactly. It feels like it's built with generalization across visual modalities in mind, not just static photos.
So it's like Qwen Image provides the missing generation piece to complement the understanding capabilities of models like Qwen 2.5 VL.
That seems to be the vision, bringing perception and creation together. The paper talks about aiming for visual language omnisystems, AI that can see, reason, and create rich, accurate, readable, visually coherent output. It really blurs that line between understanding something and being able to generate it.
So wrapping up, Qwen Image isn't just another incremental improvement. It feels like a step towards models that have a more fundamental grasp of the content they're working with.
I'd agree. It integrates perception and creation in a really compelling way.
Which leads to our final thought for you, the listener. Consider this. We're seeing a shift away from models that are just generators or just classifiers, towards systems that seem to achieve understanding through the process of generation itself. How might that change things? Not just how we make images or videos, but how we interact with information generally, how we might even define intelligence. What new things become possible when an AI doesn't just place text on an image, but actually understands the meaning of that text in that visual context, or truly grasps the objects it's manipulating?
Yeah, that's a deep question. It feels like we're just scratching the surface of what truly intelligent multimodal AI could do. Lots to think about there.